Okay, I'm ready. Are you guys ready? Okay, remember, from this part on boundary value problems, finite difference method, there will be one question in the final exam. So I'm kind of giving you a hint as we go along. We're going to continue to look at the fin problem that we started in the last class. And then I'll move on to generalization of that to nonlinear problems. So far this is a linear problem. So the key point that you have to get from what we have seen in the last lecture is if you are given a boundary value problem, okay, obviously you can use BVP4C with very little effort. All you need to do is write two small functions, one describing the differential equation, the other one the boundary conditions. And BVP4C does the remaining for you with very good control over the errors. But we are now focusing on what kind of ideas go into such algorithms. And I'm trying to reinforce this idea that we need to understand what is in the algorithm, but there are powerful tools that have been implemented in Matlab and in other tools that progressively make our job easier. Okay, FSOL, the Newton method, is another example like that. FSOL is fairly trivial to use as long as you define your problem. So in this particular assignment, you have to write the 14 functions, and FSOL can do it. Whereas if you are implementing Newton method yourself, you need to figure out what the Jacobian is and write another function for that. And you need to write the Newton code also. Okay. So in the same way, we are now seeing how to discretize the problem. That's the basic idea. Given a continuous differential equation, how do we convert that into a system of algebraic equations? If the original differential equation is linear, you will get a linear set of algebraic equations, like t times x equals b. That's what we saw in the last class. There are many variations that you should be able to handle on that. The basic idea is the discretization, constructing the grid, replacing the derivatives by numerical derivatives. And that process converts it into an algebraic equation. And in the last lecture, we looked at this basic idea of the method of finite differences, and we examined two cases for the fin problem. The model itself is given by this equation, and the two cases, two variations, are when the tip temperature is given or when the tip is insulated. That is, the derivative is specified as 0. And we completely finished the first case, and I'm going to continue with the second case where we have a tip that is insulated, implementing it in Matlab. We actually derived the equations as well. And deriving those equations are the ones that I would expect you to be able to do in the exam. Okay? And of course, if I give you a piece of code, you should be able to understand that code and fix errors in that. And for that reason, I'm going to go through the code implementation for both of them. And the other things that we learned from the last lecture would be to increase the accuracy of your numerical solution, you simply decrease the step size. That means you increase the number of points. And we went on this exercise from 100 to 1,000 to 10,000 to 100,000. And we learned something, hopefully, from that experiment. The first thing that we learned was if you construct a huge matrix, 100,000 by 100,000, that will require about 10 million storage locations for the matrix, and the computer soon runs out of storage memory size. But sparse matrices, that's where we introduced this idea of a sparse matrix. I didn't really show you how to implement it. Today I'm going to go through that a little bit in detail. And once we did that, we could increase the problem size to 1 million, if you like. And so we are able to hopefully progressively get more and more accurate results. But we saw that that was not happening. Experimentally, when we ran that for 100,000 and then to 1 million, we saw that the error was kind of getting stuck about 10 to the minus 7, 10 to the minus 8. And these are the questions that I would probe you in the first part of the exam questions, or short questions. Okay, why does that happen? The reason is the competition between the round-off error and the truncation error. The truncation error should continuously go down as you decrease the step size, as you increase number of grid points. But the round-off error is the error that you get in multiplying two numbers imprecisely. Okay, so if you take, for example, 1 over 3, you need infinite precision to actually exactly represent that. So if you're rounding it off at 15 digits and then you're multiplying another number that is rounded off, the error starts creeping in at the 15th decimal place. And if it's only two numbers, it's fine. It's going to remain in the 15th decimal place. But if you're doing 200,000 calculations, and in every calculation you have an error creeping in at the 15th decimal place, that's going to propagate into the 14th, the 13th, the 12th decimal place, etc. So the more number of calculations you have, the more the round-off error is. And that's the reason why, as we are continuously increasing it, the round-off error was plaguing our solution. So we are not able to get anything more accurate than about 6 or 7 significant digits. You can ask the question, are there ways of overcoming that to get 15 decimal places? And obviously there are. These are the iterative methods like the secant method, the Newton method, because the iterative methods have a built-in ability to get rid of errors. In fact, our first guess is a poor guess for the solution, so there's a huge error between the solution and our first guess. And the iterative methods tries to get rid of that, going towards that solution. So there is a whole class of iterative methods for solving linear algebraic equations, which we are not going to go into because of lack of time. Okay, but these concepts at least you should be able to understand. Any questions on those so far from the last lecture? Okay, so these are the equations, and we put them in dimensionless form, and these are the equations that we discretized. Okay, for case A, the temperature at the base is always 1, the temperature at the tip is 0. For case B, the same equation and the same boundary condition at the base of the fin, but at the tip of the fin, we have the derivative is equal to 0. So we need to replace, wherever we have derivatives, we are going to replace it by difference approximations, numerical derivatives. And you need to be able to choose the right ones. Okay, so for the derivative in the differential equation, we use the central difference. And for boundary conditions, you will be forced to use either forward or backward, depending on which boundary that you're dealing with. If you're dealing with the right boundary, this actually should have been 1. Right? At the right boundary, then you are supposed to use the backward difference approximations, because that's where you have the data point. So the right boundary would be something like this. This is I equal to 1. You have a grid point there, a grid point there, and a grid point there. Okay, so we label them as n minus 1, n, and n plus 1. Okay, so you're going to use a 3-point backward difference formula. You can ask why a 3-point difference formula? Because the truncation error in this formula was of order h squared. Okay, so you want to keep the truncation error in this also of order h squared. It's only the 3-point formula that gives you order h squared. If you use a 2-point formula, it's also an approximation to the first derivative, but it will give you an error of order h. That means the entire solution is limited to error of order h. So the error is not going to go down as fast as you increase the number of grid points. And then we said, okay, now that we have the temperature at every one of those discrete data points, how do I evaluate the efficiency of the fin? The efficiency is defined as the actual heat transferred divided by the maximum that is possible to transfer using that fin. Okay, and that we already have an expression. You should be able to understand and develop these. Okay, so these are the expressions for the rate of heat transfer. You will see this again in a heat transfer course. And all we are doing is putting them in dimensionless form. And when we do that, you'll get the efficiency as simply the integral of the theta values. That is the area under the curve. So for this method, what we are going to do is plot theta versus psi between 0 and 1. And whatever the temperature is, just calculate the area under the curve. Using trapezoidal rule, using those discrete values that we have obtained as a solution to the differential equation. Now for the second method, all we are going to do is minus 1 over m. M is a known parameter, and you replace this by your backward difference formula. Okay, and that backward difference formula is 1 minus 4 and 3. Okay, so 1, which is theta n minus 1, minus 4 theta n plus, what did he say, 3? I have a very poor memory. Okay, 3 theta n plus 1, something like that. So that's going to be, I just made a mistake. I want to see whether we can correct that. To calculate the efficiency, I need to calculate the derivative of the temperature at the base of the fin. That is at psi equal to 0. Yeah.
Oh, okay. I was going to ask why you
Yeah. I made a mistake. That's a mistake. I take it back. To calculate the efficiencies. Now, maybe if I made a mistake, I should repeat that to clarify it. To impose the boundary condition on the right boundary at psi equal to 1, we need to use the backward difference formula. Okay? But to calculate the efficiency, which requires you to calculate the derivative. Okay? In the right hand side, in the boundary condition, you are imposing the derivative to be equal to 0. There you use the backward difference because it is applied on the right hand side. Okay? But to calculate the efficiency, we need the slope. When the slope is non-zero, that means finite amount of heat is entering the fin from the base of the fin. So this has to be evaluated at psi equal to 0. So it must be the forward difference. Where is the eraser? Okay, it must be the forward difference that will include theta 0, theta 1, and theta 2. Don't quote me on the coefficients. The sign of that I think is probably different. It should be minus. This should be plus, and that should be minus, I think. We will verify that. It's in the code. Okay, so you must use the forward difference formula at the left boundary, that is at the base of the fin, to calculate what the derivative is. The derivative is not going to be 0. That's what gives you a finite efficiency. So there are two ways of calculating the efficiency. They should be the same. Why? Particularly in this case where the tip is insulated. Whatever the heat that is entering the fin, which you calculate from the derivative, must equal to the heat that is dissipated from the top and bottom surface of the fin, which is what the integral evaluation allows you to do. So under steady state condition, they must balance. So you must get the same efficiency. But we are going to use a numerical way to calculate this efficiency. Okay? If you do it analytically, you will get exactly the same expression. Whether you take the derivative or whether you take the integral, you should get exactly the same analytical expression, which I've given you in the last notes. Okay? But numerically, my question to you at this stage is, knowing what you know about numerical differentiation and numerical integration, you're going to get two numbers, and I will show you what those numbers are when we actually do it. But before that, I want you to think about it. I'm getting two numbers after I've solved for the temperature profile. I put it through the trapeze function, evaluate the integral, and I get one number for the efficiency. Then I use the forward difference to calculate the derivative, and I get another number for the efficiency. Will these two numbers be the same? When I say the same, you should ask me, what do you mean by same? Am I expecting it to be agreeing to infinite number of precision? Okay. Well, why would it differ?
Well, the integral is going to smooth out the errors.
Exactly. That's the idea that I kind of seeded in your mind when you were talking about numerical differentiation and integration. I'm glad that at least one person is kind of can relate to that. So most of the things, when I'm talking about many different ideas, I'm trying to sow the seed in your mind so that when you come across these problems in future, at least you know, oh, we talked about it. I can go and, you don't have to remember it, but you can dig it up and find out. Okay? So an important lesson in any numerical solution is when you are doing an integration, it has a tendency to smooth out the errors. Okay? So it will always be a more accurate operation. And we saw precisely why that is when we were developing from the Newton polynomial, the Simpson's rule, and we were developing the various differentiation rules. So numerical differentiation always exaggerates the errors, amplifies the errors. Okay? So the number that you're getting from the numerical derivative for the efficiency will be more prone to error than numerical integration errors. Of course, they should converge, meaning they should agree to maybe 3 decimal places and then 4 and then 5 and then 6 by doing what? How can I make these two numbers agree to progressively more number of significant digits? By simply increasing the number of grid points, by decreasing h, because h determines the error, right? So if you decrease h, then you are decreasing the error. That means these two numbers should agree to more significant digits. And you will see all these things happening when we are doing this particular problem. Any questions? I'm going to do it in Matlab right now. But before I do that, do you understand the basic concepts that we are discussing? You know, I don't like absolute silence. That means... Do you want me to repeat any of what I've said? No? You're all okay? All right. What do you think this is? Sparse matrix. Very good. Immediately it struck in your mind. Okay? You have done this before. This is going to be the structure of the sparse matrix for this problem with an insulated tip. Okay? For the previous problem, for the case A, where we had the tip at a specified temperature, what was the structure of the matrix that we saw in the last class? It was strictly tridiagonal. And if we put n equal to 10, you will get a 10 by 10 matrix. Okay, because there are 10 unknowns. Both the boundaries 0 and n plus 1, that is 0 and 11, are known values. But when you have an insulated tip, the 0 is still known, theta 0 is still known, it is always 1. But on the right hand side, we don't know what the temperature is, because the profile that we are going to calculate may look like this or may look like that. So the temperature at the tip is going to depend on the value of m that we put in. It's an unknown. So the unknown set increases to 11. Instead of 10, we have 11 unknowns. Okay? And we have to have the 11th equation. So the 10 equations that you would have constructed would have been these, along the diagonal, all the way up to 10. Okay? And then one above the diagonal, all the way up to what? In row 9. Okay? Because if you label these rows, you will find that it is 1, 2, 3, and this is 10, and that would be 9. Row 9. Okay? So above the diagonal, you will have the numbers going from, if it is a row number, it will go from 1 to 9. If it is a column number, what will it go? What will be the range? Yeah? 2 to 10. I want you to pay attention to these because you need to understand this before you can code it in Matlab to construct the matrix, which is no longer tridiagonal. Okay? And we want to do this as a sparse matrix. So I'm going to show you how this is implemented in a sparse matrix without using the tridiagonal matrix builder, because this is no longer a tridiagonal matrix. Okay? But the sub part of it is, if you take it up to this point, it is still tridiagonal, up to 10. So there is 11th equation that we added. And where does that equation come from? The boundary, right boundary condition. That is the 3-point backward difference formula. That includes theta n plus 1, in this case theta 11, theta 10, and theta 9. Remember, going across, it's always the variables. Going down, it is always the equation numbering, as you are doing in the current assignment as well. If you make any mistakes there, the structure will be wrong and it won't work. Okay? You have to order the equation in a certain way and put out the elements along that. So if you go down the row, each row represents one equation. If you go across the column, each column represents one variable, starting from theta 1, theta 2, theta 3, etc. Okay? So the range for the upper one for row will go from, maybe let me write it down, okay? Upper. The row range goes from 1 to n, okay? And the column range goes from 2 to n for the tridiagonal part. And then we will come back and handle this exceptional case. Okay? And then these two are the exceptional cases that we need to handle. So we're trying to figure out what are the ranges. For the diagonal element, it is 1 to n, both for column and row. Okay? For the upper one, the row goes from 1 to n minus 1, right? 9, 1 to n minus 1. And the column goes from 2 to n. What I mean by that is, are you guys following what I'm trying to say? I'm trying to figure out what are the indices range for this matrix. This is going to be the matrix that I will have to assemble for the second case. So on the diagonal element, it is 1, 1. The last one is n, n. There must be more below. There must be one more below, I think. Let me see. Yeah, there must be one more below. Thank you. So up to 10. I picked n equal to 10, so I have 11 equations. So on the diagonal, it goes from 1 to 10 and 1 to 10. That is this LO1. On the upper diagonal, on the row, it goes from 1 to also 10. This part is 10 by 10, and then I have the 11th row and the 11th column that I need to add. Okay, so I can actually make it go all the way to n minus 1 in the row, and in the column it will go from 2 to n, 2 to 10. Okay. That's what I was trying to figure out and write it here. Similarly, for the lower one, you tell me. For the row, what will be the range? Now I'm talking about this. Exactly, from 2 to 10. Oops. It starts at 2 for the rows. It starts at 2 and goes up to 10. So that's going to be 2 to n. Okay, and for the column, what will be the first column on the first element there? 1 to n minus 1. Okay, and I want to keep it as n minus 1 because I want to build it in such a way that I can change n to anything. Okay, these are the ranges for the 3 elements, and I'm figuring out only these 3 diagonal elements because everything else is going to be 0. I'm going to use the sparse solver to construct the matrix. Okay, any questions on what I'm talking about? And then I need to explicitly state what this element is going to be, and that's going to be 1. If you know the numbers, these are all 1s. Okay, and these are also 1s, the lower ones. And the diagonal ones are minus 2 plus mh squared, which we figured out by the discretization. Okay, so these are the numbers that we need to put in those locations. And the reason I need to figure out locations is because I'm going to use the sparse solver, which requires me only to tell what is its I value, what is its j location, and then what is the actual value of the content in the place. Okay, for every non-zero element, I focus only on non-zero elements. Every non-zero element, what is its ith position, jth position, that is row and the column, and then what is its value. If I enter these 3, then sparse solver will take care of all the rest for me. Okay. And of course, I need to take care of these 4 elements explicitly, and I know what those elements are. This element, for example, is going to be n plus 1. And these elements are going to be n minus 1, n, and n plus 1. Okay, so this will be, for example, theta n minus 1, theta n plus 1. And the coefficients will be 1, minus 4, 3. Those are the coming from the backward difference formula. And this, in fact, is the matrix that we developed in the last class using the last one. Okay. So going all the way up to n plus 1. On the right-hand side is just 1 in the first element, everything else is 0. Okay. This you need to figure out on a piece of paper. In an exam also, you need to discretize and you need to assemble this matrix like this. Okay. In an exam, that's where you stop. But in an assignment, you progress to implementing the particular structure. So let me open up Matlab. Are there any questions on what we have talked about so far? So there is a lot of work. That's what I want you to get, that it's not a trivial task, but it is a lot easier than what it was 30 years ago when we didn't even have Matlab. Okay? With Matlab, you can still figure out and get a solution because we have sparse solvers, we have other tools that are built into it. So our problem is focused on understanding the problem, because only we know what the problem we're trying to solve, and formulating it in a way that Matlab can handle. Once we do that, just like we saw, for example, in HYSYS, what does HYSYS do? HYSYS essentially assembles all the equations, whether it's a distillation column or a flash drum or an absorption heat exchanger, and solves those equations. Okay, but you don't even need to write a single line of code. That is the next evolution in the evolution of using computers for designing any processes. In the same way, there is a tool called Comsol, which does that for you for differential equations. Without writing a piece of code, you could set up the same problem. And I will show you how easy it is to set it up without code, because coding is not for everybody. Some people enjoy it, but others detest it, right? So we recognize that, and there is an industry that is evolving, building these tools to make our life as engineers easier. Okay, so let me go to Matlab. And here is a function that I have already written. Okay, and I want you to just understand. It's essentially building on what we did in the last class. Okay, and it takes only one input, which is the number of grid points, and the number of unknowns is always going to be one more in this particular case, because the tip of the fin temperature is not known. Okay, so if I pick n equal to 10, I will get 11 answers going from theta 1 to theta 11. Now, obviously, you understand, I guess, line 5 to line 11. What are we doing in, particularly line 10 and 11? What are we doing? I'm figuring out my h. I called it here delta x in line 10, but that is 1 over n plus 1, as we saw in the last class. Okay, and then I'm calculating, I guess, what I called m. I'm calling it here alpha, which is hp L square over ka. In the next line, because it is not tridiagonal, I cannot use that function trid that I built. So I need to rebuild that matrix inside this function itself. Okay, so I'm calculating, I'm setting a value called L equal to 1, which is going to represent the lower diagonal. And then U equal to 1, which is going to represent elements in the upper diagonal. And then D is the element that goes on the diagonal itself, which is minus 2 plus alpha times delta x squared, which is m times h squared. Okay. It is lines 16 and 17 that I spent all the time explaining to you why we need to figure out that index. Now, what you need to understand is this function sparse is a built-in function which will construct a sparse matrix for you. Once the matrix is constructed, the T is constructed, the solution is exactly the same way as you would do before. Okay, so T backslash B. Once you construct the matrix T, it could be dense matrix, full matrix, as we did in the last class, or it could be a sparse matrix. Okay, but the same operator backslash uses Gaussian elimination to get the solution using the sparse matrix. But T is stored in a different way. Okay, the way that T is stored internally is it ignores all the zero values. You tell me what are the non-zero values. You have to tell me the location and the value, and I'll keep track only of those. So in order to construct T by sparse, you need to give sparse 3 input arguments. The first one is I, which is the row location of every element. So it's going to be a huge vector. And how many elements will there be in that vector? As many elements as there are non-zero values in your matrix. Okay, so the length of I, the length of J, and the length of S will all be the same, and that length will be equal to the number of non-zero elements in your matrix. Okay, so I need to construct this I and J and S, and that's what I'm doing in line 16, 17, and 18. So with that, see whether you can understand it. What am I trying to do in I? 1 to n. What will that do? It will create a vector from 1 all the way up to n. So if n is 10, it's going to create a vector called 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and the next one goes from 2 to n minus 2 to n. So it's going to construct another vector and append it to the previous vector. It's going to go from 2 to n. Okay, so what would that represent? 1 to n is going to represent the diagonal elements, because diagonal element range is 1 to n. What would be 2 to n? Lower diagonal. Very good. You're keeping track of what we talked about earlier, right? And then 1 to n minus 1 would be the upper diagonal. Those are the row locations for every element, okay? And then these are the special cases, n plus 1, n plus 1, n plus 1. Why does n plus 1 occur 3 times? Because I have 3 entries in the last n plus 1 matrix, okay? So here is n plus 1, so I have to specify what this is, and what this is. And then I also need to specify what that one is. These are the 4 special cases. Everything else is 1 to n, 2 to n, and then 1 to n minus 1, and the above, okay? You need to spend some time with this because I'm going to put the code, and I hope you'll get the time to study it. It's likely a very similar problem where I mess up these indices and ask you to figure it out in an exam. I give you all the code, but the only place I can mess it up is here, so that you have to figure out what the right index range are. So if you don't understand it, please do ask me at this stage, okay? So those are the, so I'm going to get, in fact, I will show you by stopping inside the debugging, taking a small problem to see what the matrix structure looks like, okay? So that gives you the ith position of every one of those non-zero elements. I do the same thing for the column position, 1 to n minus 1, and 2 to n. And then I construct S. S is going to contain the actual values in those locations, okay? So I create a vector of 1s and multiply it by the diagonal. And then I create a vector of 1s of length 1 less, n minus 1. And I multiply that by L, the lower one, and then the other one by upper one. And then I put these 4 coefficients, 1, minus 4, 3. These are the ones that go in the last n plus 1 row. And then this is the value 1 that goes in the other exceptional case, slightly above. So let me just set a breakpoint here. And okay, let me go through this. When we run it, we'll come and stop there and see what has happened. What does line 20 to 22 do?
That basically on the plot, it will, wherever there is a non-zero element, it will put a spot.
That's exactly how, in fact, I generated that graph, right, that I showed you earlier, okay? So I don't want to do this when I have 100,000 because it's going to be a huge display. It won't fit on the screen. So if the size is small, I want to learn how the structure looks like. So print out that graph, which shows where the non-zero elements are. So this is also a function that you used in one of the earlier assignments. It's called SPY, which takes T, analyzes it, and shows you what are the non-zero locations visually. Okay, so it's going to create a graph. And then line 23, I think you can understand that. What am I doing there? Building the right-hand side array. Okay, so the first element is minus 1, everything else is 0. And then I'm finding the solution. Okay, that's exactly the same as before. And then I'm plotting the solution in line 26. And in line 27, the error. I'm calculating the error between the analytical result and the numerical result that I have computed in this array theta. Okay, and the analytical result comes from Wikipedia solution. You should check that one. Okay, and what am I doing in line 31? Calculating the integral under the curve to calculate the efficiency. There is a trapezoidal rule, the function TRAPZ. And then in line 32, I'm calculating the efficiency from the derivative equation using the forward difference formula. Okay, theta 1, theta 2. Okay, and of course, theta 0 is just 1. Okay, so minus 3 times 1 plus 4 times theta 1, theta 2 divided by 2 delta x divided by alpha. And these two efficiencies should agree. Okay, and that's the end of the program. Any questions on the program? So how do I run this program? Fin in step. Let me just put 5. I have 5 grid points, internal grid points. So a total of how many unknowns? 6. Okay, so I have placed the breakpoint here to show you. Maybe before I do that, I should show you, step through this and show you the figure. So we talked about having 5 internal grid points. So the size is going to be 6. You can see the matrix is 6 by 6. Okay, this is the 6 by 6 element, and it is not tridiagonal, right? So how did I construct this? I constructed this by calculating these indices of I. So before I show that, I guess you might have seen it. How many non-zero elements are there in here? 17, right? And so the index I, ith position of each one of them should contain 17. Okay, so there are 17 elements there I've constructed. Okay, and those numbers are 1, 2, 3, 4, 5. The first numbers, if you see, and then you'll see the number going from 2, 3, 4, 5. Okay, and then it is 1, 2, 3, 4. So each number from I will be paired with a number from J. Okay, so for example, I is 1 in the first element, and what is J? J is also 1. So that says the value of T11 in the first location is going to be given by what is contained in the first position of S. I hope that makes it clear now. What is the connection between these? Okay, so we construct a range of I values, a range of J values, and the range of S values, and each one will be paired. The first element from I, the first element from J will give you the IJ pair, and the first element from S will give you the actual value. In fact, you can see that if you go to Matlab and type T. The way it prints T now, previously it will actually print a tridiagonal matrix, but now it prints only the IJ pair. 1, 1, its value is 2, 1, its value is that, etc. Okay? With that one, let me ask you a question. 4, 6. What would be the sixth position in vector J? I is the row index, J is the column index. Okay, and in this particular one, this is I, this is J, the second one is J, and that is S. My question to you is, if I take a look at it, I'll come back and show you this. If I type J6, what am I going to get?
Sorry.
How did you figure that out? You are right, but I want to make sure that everybody understands that, right?
You would
You would simply go down.
And you take the product of all the elements in the J equals 6. In 6 columns, so in this case it's just 3 and 1. Multiply those two, you get 3.
It's a complicated logic. The answer is a lot simpler than that. You're right, I think. Yeah. Exactly. That's all you do. Count down 6 places in that. Because the sixth position of J is this. Okay. If I ask you what will I8 produce, okay? 2, 4, 6, 8. I8 is going to be 4. If I ask you what will S8 produce, S8 will produce this. Okay. So what we have done is we have constructed I and put the first set of numbers in that I. Then construct a J, and you put the second indices in that vector. Okay, and then a third vector that contains the actual S values. Okay, so if I, what did I get? That's not right. J, wow. Let me type one J. One, 2, 3, 4, 5. Oh, 6. Maybe I didn't count that right. Okay. I stand corrected. I need to go back and I have to look at how I ordered it in here, I think. J is 5, so J6 should be 1 here, right? Okay, J6 should be 1 simply because I pick n equal to 5, right? So I put 1 to 5, and then the sixth location, it is 1, okay? And then it starts counting again. But what Matlab has done in printing T is not printed in the same order that I have packed. Because for Matlab, it really doesn't matter. Okay, when you're presenting it like this, it resorts it, and then so it is not. So I take that back. It's not really the information in I is contained from the first column here. Information in J is contained in the second column. Information in S is contained in the third column. But they're not in the same order that I packed. It can sort it. It can shuffle it because the reason is it is the number that actually matters. 4,4, position 4,4 contains this value. Whether I print it here or I print it there doesn't matter. Because it simply says that the 4,4 position contains the value of minus 2.0278. Okay? So I think what Matlab has done is in printing that, it has kind of resorted it, and I have to see whether there is a method to this madness of how they sorted it out. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Okay. I can see a pattern. What is the pattern? They've sorted by second one first. 1, 1. So they take J and they sort it on that. And then they take I and they sort it on that again. Okay? So it's 2, 2, 2, and then 1, 2, 3. 2, 3, 3, 3, and then 2, 3, 4. You see all the 4, 4, 4, 4, 4 in the same order. So they have reordered the elements in T, but it does not change the location. The location is contained in actual values. The number that is contained in here, 5 and 4. T, 5, 4 will contain that number. Okay. So let's go back and continue this execution. Okay, now I constructed B, I constructed theta, and there is my temperature profile using 5 points. Okay, and you can see that the temperature gradient is 0, and the temperature tip of the temperature is not at 0. It is at higher value, 0.65. It's actually pretty hot, right? And now we have to focus our attention on how we can get more accurate results. We understand the process of setting it up, and I learned something about T, how Matlab sorts T just now. But we need to continue this by calculating the efficiency from the integral and derivative method and print it out and see what those values look like. What would you, what do you expect? Here it is. From integral, it is 0.76. The efficiency is 0.763. And from derivative, it is 0.754. Which one would you trust more? The integral. Okay. But the error is in the second decimal place because they don't agree in the second decimal place. They agree only to the first decimal place. You can be confident that it is 0.7. Is it 0.75 or 0.76? You don't know. Okay. So what you need to do is increase the number of grid points. So let me continue and get rid of the breakpoint and simply rerun this case now for 200, for example, and I put there. So that is a solution with 200 grid points. So the step size is 1 over 200. Okay, and it's not going to print the matrix anymore for me because I suppressed it. But let's look at the answer. Fin efficiency is 0.7615. So with 200 points, inverting a 200 by 200 matrix, we are able to get results that are 4 digits accurate. Okay, they agree. Both the integral and the derivative method agree up to 4 significant digits. But the actual temperature value is actually even more accurate because this is comparison with analytical result. You can see up to 6 significant digits, you get the accuracy. Okay, but because we have used the sparse solver, we can very easily increase it to 200,000. Seven six one five nine, 76159, 5 significant digits. Why did not the accuracy improve when we went from 200 to 200,000? Rounding errors once again. Okay, you see that problem. As the number of multiplications and divisions increase, the round-off errors increases, and that begins to control your solution. So you cannot get simply increasing the size, you cannot get more accurate result. Any questions on that? Okay, what would you need to know from the point of final exam? given a differential equation, boundary value problem, I might ask you to develop the discretization of that, identify whether it's linear or nonlinear, etc. And then given a piece of code, try to fix it to make it work. Okay, so you should be able to do these two aspects. Let's move on to the next problem. Oh no, before I go into the next problem, let me continue with this problem and illustrate how you would solve this problem using Comsol. Now, there are certain things in this course I have done with very brief exposure. The purpose of it is not to examine you on that. I will never examine you on HYSYS or Comsol, okay? But to show that these such powerful tools are built on what we have seen in this course and are going to be extremely useful for you in the future in other courses. Comsol is a package. It's a graphical user interface driven package that solves any differential equation, ordinary differential equation or partial differential equation without programming. So it's like HYSYS for algebraic equations for differential equations. Comsol is available in all the computers in chemical engineering only. Okay, just like HYSYS, these are software that only chemical department has licensed. So if you go to chemical engineering lab, you should be able to see this particular icon and then start Comsol multiphysics. It's going to take a while to open up. And I'm going to get those same graphs without writing a piece of code, but making choices, okay, for defining the problem. So it is still up to me to define the problem because these are general purpose tools. Okay. Okay, so I need to define the problem. So when you start Comsol, this is the GUI that you get, the graphical user interface that you get. Okay, and it is structured in such a way that it takes you through the steps of defining the problem. The first thing that you need to tell Comsol is, am I solving a one-dimensional, two-dimensional, or three-dimensional problem? What do I mean by that? What do you understand if I say it's a one-dimensional problem? The number of dimensions in which the independent variable is changing. Okay, in this course, we have seen the classification of lumped versus distributed, steady state versus dynamic. Okay, so if I have a steady state, I can do both steady state and dynamic in this. I'll show you how that is done. And it is primarily meant for distributed problems, not lumped problems. Lumped problem, you have HYSYS. Okay, so distributed problems, so you'll have to have the variation of the dependent variable at least in one dimension. So if it is in one dimension, then you will say 1D. If it is in 2 dimension, you will select 2D. If it is in 3 dimensions, you will select 3D. Okay, the 3D could be you're designing a furnace in a plant. Okay, so you want to determine the heat transfer from all the furnace walls. So it's a 3-dimensional object. So CAD will help you in importing the actual geometry into this program. And then you'll specify the differential equation and the boundary conditions. I'm going to do just for 1D because I have only a fin in 1 dimension. It's an ordinary differential equation. Once I select that, if you see the pattern, it says next. Okay, or if you select this one, it says finish. I'm finished with that. But let's go through the step of next. What next? Okay, so it will guide you through the process. The next thing it will ask you to do is, okay, you have some problem in 1 dimension. Tell me a little bit more about the problem. What is the nature of the problem? Is it a fluid flow problem? Is it a heat transfer problem? Is it a mass transfer problem? It's a chemical reaction engineering problem. So that you select. So this is called, it says add the physics. What is the physics that you're trying to determine? So in our case, we're going to do heat transfer. And when I select that, it gives you many options. Is the heat transfer taking place in solid or in fluid or in porous media? Packed reactors are very commonly used, right? So I'm going to say solid, simply a heat transfer in solid. And then I've selected that. And I want you to watch what happens here. This is called the model builder area, where you're building the model by making these choices. Okay, the model wizard takes you through the process of identifying the right set of equations, boundary conditions, etc. So here I have selected heat transfer in solid, and I go to the next one. When I say next one, it says, okay, what kind of a problem is it? Is it steady state or dynamic? So that's what this one is. Stationary means steady state. Time dependent means dynamic. So in my case, I'm going to select steady state because I have a heat transfer in a steady heat transfer in a FED. So I select that. There is no more option. So this becomes disable, and I finish that. Once I finish that, it immediately adds all the choices that I have made. Now I have a heat transfer. I've not written a piece of code, okay, but I've already identified what equation I'm solving. How do I know which equation I'm solving? I go and select that, okay. Here, it tells me I needed a bigger screen space, but once I select, these are all folders. Into folders, I'm building the model, okay. So once I build the heat transfer model, I can come and look at the equation. This is the equation I'm going to be solving. Does this equation look anything like the Finn equation, the equation that you see there? It does if you make the left-hand side equal to 0, and if you make Q as equal to m times theta. Remember, the original equation that we had, in class, there's no shot. So, okay. So the equation that we are trying to solve is this. Okay, and theta at psi equal to 0 is 1, and theta at psi equal to 1 is 0. That's the case A. This is the equation we want to tell Comsol to solve. Okay, but the equation that you see there is going to become like that if I make this 0 by setting the velocity as equal to 0. There's no motion, and I set Q as equal to minus m theta. I need to do those things. Okay. If there are any questions, please do ask me. And the other thing I need to do is, once I have identified the model, I need to tell the geometry, the domain that I'm interested in. The domain I'm interested in is one-dimensional. This is psi going from 0 to 1. And I need to put a set of mesh. We have seen all these ideas, and we are going to implement those ideas without writing a piece of code. Okay? So I need to now go to the geometry. And it says, what is the geometry? I don't have any information about the geometry yet. So you select the geometry, immediately it gives you certain menus there, okay, to construct what the geometry is. You can construct a rectangle, a circle. In this case, it's just a line, okay. So I'm going to take that line and start from 0 to 1. I draw a line. Oops. Come on. I click the point at 0 and then take it to 1. And what do I do? Okay, there. Okay, the interval. So then I go to the interval and it tells me the left point is at 0, the right point is at 1. So it's just filling out forms in defining the problem. Okay. So now I have identified my domain going from 0 to 1. What would be the next step? I need to construct the mesh. Okay. So there is a folder for constructing the mesh. Okay. And when I select that folder, it says, okay, what kind of mesh do you want? I say physics control, meaning you decide whatever it is. But when I select that, it says what is the normal element size. So you don't have to specify a number. It says make it normal, make it fine, or extra fine, or extremely fine. So I say, okay, extra fine. Okay. So it really makes it very simple for us to do. So once I do select that, I say go and build the mesh. So it has built the mesh for me. Okay. And how do I know it has built the mesh? It gives me the information here. Mesh consists of 50 elements. So it has divided the domain into 50 elements. If you go, you can select extreme fine, maybe it will divide it into 100 elements, for example. Okay, but this is equivalent in our Matlab code to determine what h is, 1 over n plus 1. Okay, so that's what we have done so far. Any questions? Okay, now I need to specify that the heat transfer is in this domain. So each domain is labeled with a number. Okay, so domain number is 1, and in that domain I have the heat transfer in solids, and the heat transfer model is that. Okay, so this model requires me to specify the values for K, the thermal conductivity. So I'm going to select that and say user define and just put a value of 1. Okay, so my thermal conductivity is 1. Remember, I had 5 parameters in the original problem. I need to specify all of them. So another thing, in order to define all the parameters in your problem, there is this global definition. So if you click that, parameters, right click that, parameters. So it gives you a table where you can define your variables. For example, HH, and its value is 1. Okay, and then you go K, and we said its value is 1. And what else do we have? P, its value is, I'm making all of them 1, but you can change it to anything that you want. Okay, and what else do we have? H, L. Length, of course, we have made it as equal to 1. Okay, and then I'm going to calculate M. Okay, so I'm going to calculate M, and you can put any expression that you want here. The M is H times P times L squared divided by K times A. So this parameter allows you, no matter how complicated your model is, all the symbols that are appearing there that have constant values, you put it in the table, and it will automatically pick up in those equations. Okay? Pardon me?
Wouldn't it be HH times P times...
Yeah, thank you. Thank you. Otherwise, I would have an error there. Oops. Right. Okay. Now, Comsol has a link to Matlab. So instead of putting an expression, if you want to put an M file there, that's perfectly fine. It'll just go and pick up the M file and evaluate whatever is in there. So it's really a very powerful link between Matlab and Comsol. Okay. So I have defined so far all the parameters that are appearing in the problem. What else do I need to define? I need to define the source term, the heat, this term in the equation, Q. Right now it is just a symbol Q. Okay. So I go and right click on this and say add a thermal source, heat source. Okay. Then it adds another folder. So the building process for the model is add as many folders as you need here, defining everything in this equation. So every folder is like writing any line in your Matlab code, if you like. Okay. So the heat source is going to be applied in this domain 1. So I add domain 1. In that entire domain, there is a heat source Q term, and the Q term is defined as minus M times T. M is what I have calculated in the parameter space, and T is my unknown variable. Okay. How do I know T is the symbol used for that variable? In this equation, that is what is appearing here, T. Okay, so T is my unknown, and Q is what I have just now defined in the heat source term. Here is Q. Okay, so what else do I need to define? Boundary conditions. That's the last piece. Okay, so I need to specify the left boundary and the right boundary. So once again, I go back to the heat transfer model, right click, and it tells me temperature. I need to add 2 folders for the temperature. The reason is I have left boundary and the right boundary. So I select temperature 1 and I go to this and I click and add that. So the left point is labeled as point 1 and its temperature is going to be 1. So change that value. Okay. And then I take 2 and I add to that folder the right boundary. And what should this value be? 0. That's it. Okay. I've defined everything that I need to define. So I go to the study and I say solve, compute. There is my temperature profile. This is for K equal to 1. So if I want to change the question.
This would be for part A.
This is for part A, case A. Case A, right? For case B, see how easy it is. All you need to do is, this is the boundary on the right? So I can delete that, get rid of that boundary, and then there is already a folder there for insulated boundary. So identify 2 as the insulated boundary. Okay. Now in one stroke, I've changed the case A to case B. I can say go and recompute. There it is. You see the difference between case A and case B. Case A, it was almost straight. Case B is, because you need to make the gradient here 0, right, in this part. So now if I change the values of the parameters, I can get a series of curves. For example, I go to study and I right click and there is something called parametric sweep. And you can identify a parameter. So for example, I'm going to change K. Okay. And then I tell what are the values I want to find. 1, 0.05, 0.01, 0.005, etc. So now I say go and recompute. So it's going to give me the solution for 4 values of K. That is my temperature profile for each value of K. K equal to 1, 0.05, 0.01, 0.005, etc. And I did all this in about 10 minutes without writing a piece of code. That's how powerful these computer-based simulation tools are becoming. And you will use more and more of these as you, I guess, graduate and go into the workplace. This is a very quick view of what is possible. Okay, I might give you an assignment on this so that you get to play with Comsol on a very simple problem. And you can, this is recorded, so you should be able to see what it says. Let's stop there.